So we're going to start just with an example, and I want to do this example as an application of the unit vector. So that's the question that Nate just asked us about, how did we find that unit vector? Remember from yesterday we talked about a unit vector is a vector with magnitude of 1. You can get a unit vector by taking the vector divided by its own magnitude. Okay. So here's one application of when you could use a unit vector. Suppose we have the vector v, or we want to find the vector v with a given magnitude that goes in the same direction as vector u. So, pay attention here. Vector v's magnitude is 15. So this is the magnitude we want. We want magnitude 15. We want it to go in the same direction as u. So you don't always have to draw this out, but I'm just going to go ahead and draw a quick pic of what u looks like, right? 1, 2. That vector there. So we want a vector of magnitude 15 that goes that same path. Do you think u currently has a magnitude of 15? No, it's way too small. What is the magnitude of u? The square root of?
4, 5.
5. 1 squared plus 2 squared would be 5. So, as we're practicing our homeworks, we're going to get faster at things like magnitude. We might not have to show all the work every time. We can do 1 plus 4 in our head. Okay, so the magnitude of that is 5. So that's only what, 2.1, 2.2, something like that. So we're looking for v, and we really want it to be a much longer vector, right? We want it to have that magnitude of 15. So here's an application of the unit vector. Okay? Find the unit vector for u. So scale it back so it has a length of 1. And then if your unit vector has length 1 and u want a length of 15, multiply by scalar of 15. Now, I'm going to do that in 2 steps. Find the unit vector, then multiply by my desired magnitude. But some of us may think, well, I'm just doing multiplication. I could do that in 1 step, right? Multiply by the desired magnitude over the magnitude of u. Okay. But I'm going to go ahead and find the unit vector. So this is Nate's question from the homework. That will be what? 1 divided by square root 5, so square root 5 over 5. 2 divided by square root 5 is 2 square root 5 over 5. And what's special about this vector? It has a magnitude of 1 now. I left it up over here on the sideboard. I mentioned it yesterday, but I didn't show it out. But here I put in square root 5 over 5 and 2 square root 5 over 5, and I squared them. And I come up with 5 25ths plus 20 25ths, which is 25 over 25, which gives me a magnitude of 1. So it should check in the end. But now if I know that that unit vector has a magnitude of 1, I can get my desired magnitude using a scalar. So to get v, multiply the unit vector by 15. That'll get us our desired magnitude. So v equals 15 times square root 5 over 5, 2 square root 5 over 5. Well, when I distribute the 15, that's going to cancel out with the 5, so get 3. So we'll have what? 3 square root 5 and 6 square root 5? And if I checked magnitude, I should get 15. Questions? It's just a good thing for people to think about, okay, why would you ever have mentioned a unit vector? what good is a unit vector? Why would I want a vector of length 1? You can take any vector, make it a unit vector, and then scale it back out to any size vector that you want. Okay, so that's kind of like a little sidebar and one of the uses of a unit vector from yesterday. Now we're going to talk about another way to do component form. So yesterday, and like I always say this about just like reminder about vectors. The hardest part about vectors is not the actual math of vectors, it's just like knowing what it means and what you're supposed to do, right? So kind of try to break down directions and really focus on like what's it asking about, what do I need it to look like, how do I find that? So when I read this up here at the very top, it says component form. And yesterday when we did like the basics of vectors, we know that component form is v sub 1, v sub 2, right? Where v sub 1 is our horizontal component and v sub 2 is our vertical component. Now, yesterday, if I gave you an initial point and a terminal point for a vector, you could find component form by doing subtraction of the horizontal components and subtraction of the vertical components. But in this problem, see this vector I have here in blue? I'm not giving you the initial point. I'm not giving you the terminal point. I'm giving you the angle, direction angle, and the magnitude of the vector. So now, can we come up with another way to get our horizontal component and our vertical component if we know the magnitude and the direction angle? Well, think about where your horizontal component is, right? Here's my horizontal component. If I know this angle and I know the magnitude and I'm looking for v sub 1, what could I use? Cosine, Liam says. Yeah, use cosine. It's adjacent, hypotenuse, and the angle in between, right? Okay, so let's do cosine. I'll do that over here on the side. The cosine of theta is equal to what? Adjacent v sub 1 over the magnitude? Adjacent over hypotenuse? Okay, so we're trying to get component form, so we'd really like to know what v sub 1 is. If v sub 1 is being divided by magnitude v, multiply both sides by magnitude. Okay. So my horizontal component, given a magnitude and a direction, is the magnitude times the cosine of theta. Now, I think it's easiest if you just know this, magnitude times cosine, because you're going to use it and use it and use it, and so it's just faster to know it. But you could always, if you're unsure, you can always draw a trig and then figure out, oh, that's cosine. Okay? That may be what we'll do in physics. Not sure. Any physics people want to say? Did you ever learn magnitude times cosine for horizontal component? Questionable. Okay. We'll see if anything comes up later. Okay, so we've got the v sub 1, we've got the horizontal component. How will we find v sub 2? Then we're going to use sine. I'm not going to write out all of the sine stuff, but it would just be sine theta equals v sub 2 over magnitude v, multiply by magnitude v. And so our vertical component is the magnitude of v times the sine of theta. So that's our vertical component, which is v sub 2. So, yesterday we talked about v sub 1, v sub 2 was x sub 2 minus x sub 1, y sub 2 minus y sub 1. And that's if you have information like initial and terminal point. And now we're saying v sub 1, v sub 2 is magnitude times cosine, magnitude times sine. That's if you know the magnitude and the angle. Okay, in the second part on the screen here, it's asking you to give the linear combination with magnitude and direction. Well, this would be just like what we discussed with the linear combination yesterday. It has the standard unit vectors I and j. And if I think about what we talked about yesterday, linear combination is your horizontal component times I plus your vertical component times j. And so we know v sub 1 is magnitude times cosine. So I could really just write this as the magnitude times cosine I plus magnitude times sine j. Now, really, these are like bolded, right? These are like our, what do we call them, standard unit vectors, the I and the j. So just because this is going to come up later in section 6.5, that I is not imaginary I. That's the standard horizontal unit vector I, 1, 0. Okay, so now we're going to kind of shift gears, and for the rest of our problems, we're going to be working on this idea. So there was something you were like leaving the room with, and when you're working on your homework tonight, and you're focused on what's the piece that I want to know from today, this would be it. Magnitude times cosine, magnitude times sine. We'll do an example where, given this information, let's write our vector in component form. So we're given magnitude of 5. We are given an angle, direction angle, 30 degrees. We want component form, v sub 1, v sub 2. And we just said if we had magnitude and direction angle, we could get v sub 1, v sub 2 through trigonometry. Magnitude times cosine, magnitude times sine. So now I have what I need. I just plug them in. What will that be? 5 cosine 30, 5 sine 30. Okay. What does the chapter 4 student in you want to do? Chapter 4. Do you know the cosine of 30? Unit circle. Cosine of 30?
Isn't it radical 32?
Radical 3 over 2. So this is going to be 5 radical 3 over 2. Sine of 30? 1/2, 5/2. Now, I did see some people going through their calculators, so maybe you're typing it in your calculator, but I will say, if your angle is an angle in the unit circle, you already did the unit circle in chapter 4, so you can leave your answers in exact form. If this was 5 cosine 42 and 5 sine 42, I would probably just leave my answer like that, because that's exact. If you wanted to estimate it, you could plug it into your calculator, and of course you're going to get decimals because you don't know the ratios for 42 degree sine and cosine. But I like this one because it's exact. So I know on my quiz I ask for some exact, I say your answer should be exact. So that means basically use your unit circle. Even though you have your calculator in front of you, use your unit circle knowledge, okay? Which means no decimals. Now we'll also look at a second example here, kind of the same idea but a little tweak. This problem, you're given the magnitude of 2 and you want your vector v to be in the same direction as negative 2i plus 3j, this is really like the first problem I showed you, where I did an application of the unit vector. We could scale back that vector negative 2i plus 3j, we could make it a unit vector, and then we could multiply it by our desired magnitude. But on this one, we're going to use that component form with magnitude and direction angle. So there's more than one way to go about doing this type of problem. If you want an exact answer, you should use the unit vector method that we used previously, but we can also get a close answer using this method. So in order to be able to use this magnitude times cosine and magnitude times sine, you need magnitude and angle. Right now we only have magnitude. Can you find theta for this vector? Yeah, like our warm-up, number 4, right? Direction angle is inverse tangent of vertical over horizontal component. So we're going to do theta equals inverse tangent of 3 over negative 2. Let's see, you should get a negative answer in the calculator. Everybody give me that number.
Negative 56.3.
Negative 56.3 degrees. And remember, in our notes from yesterday, it says about direction angles should be between 0 and 360. So this is outside of that range. And you should make sure you're in the correct quadrant. So I would take a minute to think about this angle or this vector, negative 2i plus 3j. If I go left 2 and up 3, my vector is somewhere in quadrant 2. So if the calculator is giving me an output of negative 56.3, and I know that my vector is in quadrant 2, how will I get my actual direction angle? Could just add 180 to what the calculator is giving you now, right? It's negative 56.3, so that's going to be like 180 minus 56.3. The 56.3 right here represents like a reference angle of sorts. So we can just add 180 to it, and theta is, what is that, 123.7?
Yeah.
Which makes sense. That would be an angle in quadrant 2, wouldn't it? So now I can go back up to what I have at the top of the screen, and I can write component form. Magnitude times cosine, magnitude times sine. And I have my angle. That'd be 2 times cosine 123.7 and 2 times sine 123.7. And this is an example where, I've already rounded the angle when I did inverse tangent, because it wasn't a nice number, right? I already rounded the angle. So I'm just going to leave it in that component form. That's fine. I did this one because I knew sine and cosine of 30. So let's simplify it. This one I don't know, sine and cosine of 123.7. If I want to get the actual decimal for my horizontal and vertical component, I can multiply that through. But I can also just leave it like this. That's fine. Okay? Okay, let's try another example. You guys are going to do the work for it. Again, I can't stress enough in preparation for your quiz on Friday and in preparation for your test. I think that's happening next week. What day is that? Is it on Friday? Anybody got their gold sheet?
Friday.
Oh, it's next Friday, your test for Chapter 6. I can't stress enough the importance on these vector questions. The math is not hard, so I'm hoping people could do really well in vectors. But the hardest part is like knowing what it's asking you to do. Okay. So, as I read the directions here, something that sticks out to me is them being asked to find component form. Now the most basic component form from yesterday is V sub 1, V sub 2. Horizontal component, vertical component. I know two ways based on the information that I'm given. You know, I could do terminal minus initial for the x's and the y's, or what we just talked about, magnitude times cosine, magnitude times sine. Those are both different versions of component form. So I'm thinking about that, angled brackets, component form. And then the other thing that stands out to me is that I actually want the component form for the sum of u and v. So you guys did some, on your homework, you did some sums, right? You added some vectors together. Okay. And remember, when you're doing addition with two vectors, you need all the components of u and v so you can add the horizontal components and add the vertical components. So right away, if this is our given information, we're going to need to find component form for u, and we're going to need component form for v, so that we can then add horizontal and vertical components. Will you please do that work? And I would like my answers to be exact, no decimals. Okay, I see varying levels of comfort as I go around the room. Some people are writing down each individual step. Some people know their unit circle really well, so they're able to do some of that stuff in their head. Cool. Either of those is fine with me. Okay. When I plug this into my my magnitude times cosine, magnitude times sine, and then I evaluate cosine and sine of 45 degrees, I'm going to end up with component form square root 2 for u. And then for v, we just repeat the process with its values. And you should end up with cosine is what? 0 and sine is 1. So 0, 5. So we're just breaking down the problem. Let's find the basic vectors u and v. And now it would be really easy for us to get the component form for the sum. Add horizontal components. So what will that be? Square root 2 plus 0, square root 2. And vertical components, square root 2 plus 5. I usually write that as 5 plus square root 2, but I'm not picky about that in your final answers. Like, you could write it in any order. It's just the normal way you see radicals is at the end of an expression. So that will be my component form for the sum. Exact, no decimals. Doing okay with that? Okay. So let's see. I think I have one word problem. Then I'll hand back your quizzes. We've got a water balloon traveling with initial velocity 40 meters per second. It's being launched at an angle 60 degrees above the horizontal. And we want to find vertical and horizontal components for the velocity. So this is leading us into tomorrow, where we're going to introduce like the work and force problems. And what's important for tomorrow is that you can pick the one component that you want, whether it be horizontal component or vertical component, but you won't need all of it. Okay. So you'll need to be able to distinguish between the two. Now, on some of these, I might start with a picture, because if you don't know what to do with vectors, you can always fall back on a picture with trigonometry. So let's see, I'm launching the water balloon at a 60-degree angle above the horizontal. So horizontal would be here. This vector represents the path of my water balloon. Okay, its initial velocity. One thing to note is when we're giving you these measurements of initial velocity, those things are going to be the magnitude of your vector. So this is the magnitude of your vector v, so I'm going to label this as 40 meters per second. And then I have everything I need. I have magnitude, and I have theta, so I can find horizontal and vertical components. Now, I'm going to break them up. You could put them into component form if you want. It doesn't necessarily say that it has to be in component form, so I'm going to break it up. If I want the horizontal component, that's the magnitude of v times cosine theta. So what are we saying is the magnitude 40 times cosine 60? And since that's a unit circle angle, I'm going to use the exact value. Cosine 60 is what, 1/2? So 40 times 1/2 is 20 meters per second. And then I can do the same for vertical component. So that'll be magnitude times sine of theta. So 40 times sine 60. And that's got to be what? Square root 3/2? So 20 square root 3 meters per second. Now, if you write that out in the component form with the angled brackets, that's fine. I will always then assume your horizontal is the first value and your vertical is the second value, just like we're all accepting that to be the way that it is. So you would want to add in your labels if it's a word problem, so you put meters per second in there. Questions, concerns? Okay, your homework assignment is on the gold sheet, and I'll switch over to that so you can get those problems down if you want. You should be doing your homework for vectors. Section 6.5 next week will not be real fun for those people who don't know the basics of vectors. Okay. And I'm going to hand back your quizzes. We're going to use the yellow correction sheet that's up at the top table. So once your pod gets their quizzes back, figure out how many sheets you need and send someone up to grab them. And you'll only need to correct problems on the quiz that have been circled. A check mark is just me, because there was like a lot of things to check on the front. That's just me saying like I found that angle or that side. So a check mark is right. A circle is something where you lost points, so you want to redo that if you want points back.